Welcome. This is a video presentation of the paper, The Origin of Matter and Gravity, What They Are and Why They Exist, Part 4, Gravity. Particles and quanta are not static entities. They change with time and expansion. We previously reviewed the ideal particle. The ideal particle mass is given by this equation here. And you'll notice that we have this factor here, which is not a constant. It's R sub h stands for the radius of the hyperverse, meaning that the ideal particle mass changes with expansion. The ideal particle radius, equation given here, also carries the term R sub h, and it also changes with expansion. The number of particles in the universe is also a function of the radius of the hyperverse, and it too changes with expansion. Let's look at the effects of doubling the size of the hyperverse radius on particle dimensions. We'll use the now and then approach we used in the geometric mean paper. The word then refers to the time when the hyperverse radius was 1/2 of what it is now. Looking at how the number of particles increases with a doubling of the hyperverse radius, we find the number of particles now are RH over 2LP to the 4/3 power, divided by the number of particles then, the difference being the RH divided by 2. And we see we get 2 times the cube root of 2. So with a doubling of the hyperverse radius, the number of particles increases approximately 2.52 times. Looking at how particle mass changes with a doubling of the hyperverse radius, we can take the particle mass now divided by the particle mass then, where RH was RH over 2, and we find we get 1/2 to the 1/3 power. So particle mass actually decreases by a factor of about 0.79 with a doubling of the hyperverse radius. And we find that the radius of particles also decreases with a doubling, and at the same rate as mass. Particle radius now divided by particle radius then, RH divided by 2. And we get the same value, 1/2 to the 1/3 power, or approximately 0.79 times. So particle radius also decreases with a doubling of the hyperverse radius. The number of small energy quanta within a particle increases with a doubling. We see here our value for the number of SEQ within a particle. This is our situation now, and RH over 2 is the situation then. Calculating this, we find that the number of SEQ within a particle increases by 2 to the 2/3 power, or approximately 1.587 times with each doubling of the hyperverse radius. And this is important. We can see that the particle is accumulating small energy quanta as time progresses. We can calculate the number of small energy quanta absorbed per particle per second. Here is our number of SEQ in a particle, divided by the age of the universe, and we get approximately 9.23 times 10 to the 22 SEQ absorbed per particle per second. We can calculate the energy absorbed per particle per second. We take the last value we just looked at, the number of SEQ absorbed per particle per second, times the energy per SEQ, and we get 2C over RH times the energy of a particle, which comes to approximately 1.11 times 10 to the 29th joules per second. If we take the energy absorbed per second per particle and divide it by the energy of a particle, we put in our equations here, and we get the result of 2C over RH. 2C over RH is the Hubble constant. So particles are accreting energy, or quanta, of space at a rate equal to the Hubble constant. We will now show that gravitational potential energy accumulated per second is the accreted energy. The general equation of gravitational potential energy of mass, m, is U is equal to the gravitational constant times the product of the masses divided by the distance between the centers. And in this analysis, for simplicity, we're just going to work on magnitudes only. We're going to let both masses be the particle mass. So instead of big M times little m, we just have particle mass squared. And we're going to let the distance between the centers of the two masses be 2 times the particle radius. So the particles are just touching. We have 2 particle radiuses. So we have our particle mass squared times our particle radius times 2. And this works out to be 1/8 times the energy of a particle. So we saw that the gravitational potential energy for 2 particles touching is 1/8 of the energy of a particle. Remember, that's for 2 adjacent particles. But with particles touching on all sides, or surrounding space filled with mass, a distance of 2 radii means the volume is 2 cubed, or 8 times greater, so that the total of the adjacent mass is 8 times a single particle mass. Considering then all of the adjacent mass in the full volume around the absorbing particle, we find that U, the gravitational potential energy, matches the particle energy. We see that U is equal to the particle mass times the mass of the surrounding particles divided by 2 times particle radius. And this works out to be gravitational potential energy U is equal to the energy of a particle. And if we take the gravitational potential energy of a particle and divide it by the age of the universe, we get the same rate of addition of gravitational potential energy per second to a particle, where gravitational potential energy divided by the age of the universe comes out to about 1.11 times 10 to the minus 29 joules per second. Of course, it should be the same because U here is the same thing as the energy of a particle. We can make the claim that the gravitational potential energy added per second is identical to the accreted energy, that the gravitational potential energy divided by the age of the universe is the accreted energy per unit time. The gravitational potential energy of a particle is the accreted energy. Let's look at the relationship between gravitational force and centripetal force. In order for a vortex to spin, an inward or centripetal force must exist. Centripetal force, F sub c, was defined previously as the speed of light to the 4th power divided by 2 times the gravitational constant. And again, quickly, centripetal force is equal to the mass times the angular acceleration. So our mass and then angular acceleration is a tangential velocity squared divided by the radius. And we plug in our particle mass, our constant tangential velocity of the square root of 2 times c. Of course, we're going to square it here. Divided by the particle radius, and we get c to the 4th over 2g. The gravitational force between the absorbing mass and all the adjacent mass at 2 times their radii is, we have F sub g, that's our gravitational force, and this is the standard equation for gravitational force, so we have g, and we have our mass of the particle here, and we're going to look at it for the full surrounding volume, 8 times the particle mass, times 2 times the particle radius squared. And we find that the force of gravity is equal to 1/4 times c to the 4th over 2g, which is our value for F sub c. Our value for the gravitational force is 1/4 times the centripetal force. At a distance of 2 radii, the gravitational force is very close to the centripetal force of a particle, off by a factor of 1/4. This distance of 2 times the radius is outside the particle, and we would expect any centripetal force that existed there to be less. And let's make this clear, and we're going to go right over the top and use a thicker pen. So if we have adjacent particles, we have the radius, we're talking about this point here versus this point. So this point here is twice as far from the center as the point that we usually calculate centripetal force for from here. So, since the distance in this case is twice the distance of a radius, and given that force drops by the inverse square law, we'd expect a doubling of the distance to reduce the force by 1/4, just as we have calculated. At a distance of 1 radius, the force of gravity equals the centripetal force. So looking at the force of gravity, we take our mass times 8 times the surrounding masses, and instead of 2r, it's just radius squared. So radius squared, and we find that F sub g, the gravitational force, is equal to c to the 4th over 2g. And as a quick reminder, centripetal force is equal to the mass times the angular acceleration, and that works out to be c to the 4th over 2g. So we have our gravitational force and centripetal force are equal at the distance of 1 radius. At a distance of 1 radius, the centers of the masses are at a distance equal to the radius of a particle. And to show a picture, we have a particle with this radius. Here's the center. The center of the other particle would be here. So we have adjacent particles, but they're overlapping. The distance between the centers is 1 radius. At this distance, from the center here, the gravitational force and the centripetal force are identical. We will contend that not only are the magnitudes of the forces identical at the particle radius, but they are the same forces, simply manifested differently within or beyond the particle radius. That is, the centripetal force and the gravitational force are the same force. This greatly simplifies the situation, leaving us with just one force. Elementary particles are not static, unchanging entities. Matter is formed as a means for the expanding universe to conserve angular momentum while maintaining centripetal force. Since the angular momentum of the universe continues to increase, and the energy of quanta decreases with time, particles must change with time. We have seen that the mass of particles decreases with time, but so does the mass of the component quanta. Specifically, the quantum masses shrink at a faster rate than the particle mass. Between shrinkage of the quanta and the continually increasing angular momentum of the universe, the particle must continue to absorb quanta to conserve angular momentum and centripetal force. It is an ongoing process driven by expansion, and this is gravity. The absorbed space pulls along the matter embedded in it. The closer to the absorbing matter, the faster space moves, just like water close to a drain moves towards the drain faster than water farther away. Matter does not curve space, matter absorbs space, incorporating the quanta of space into the necessary mass and volume to conserve angular momentum and maintain centripetal force at the required constants. Particles of matter are conserving the same initial value of angular momentum and centripetal force. This gives a simple explanation for why all particles of a kind are identical. It is a dynamical process, And we see this relentless accretion of the quanta of space by matter as gravity. To understand matter is to understand gravity, as the same process creates them both. Matter and gravity exist as the result of fundamental conservation laws. Gravity, like time, is a manifestation of the expansion of space in our daily lives. Gravity exists because space expands.